I want to give you a couple more examples of integration by substitution. So to save a little time, I've already started loading a problem, and you see the integral of x cubed over a square root, 2x4 plus 3. When doing substitution, it's often the case, though not always the case, that the more complicated thing is going to be your inner function. And the inner function is often the argument of maybe natural log or an exponent on an exponential function, an e, or in parentheses that are raised to a power, or in this case, a square root. So if I'm seeing my inner function as 2x to the 4 plus 3, then it would be natural to do my substitution by letting u be that inner function. Now if I let u be the inner function, I need to calculate the differential, du. But that is as easy as taking the derivative of this polynomial function. And we've learned some time ago how to do that. So taking the derivative here, I would get 8x to the third, and then a dx. 8x cubed dx. And that's what my du would be. Well, I can only use the substitution method if I've got an integral that involves u and the du, but you compare 8x cubed to what's left over here if I let u be 2x to the 4 plus 3, and I see I've got an x cubed. Well, that's the hard part because I can't introduce an x cubed, x being the variable, but I can introduce an 8 anytime I want to. So why don't we try to rewrite what we've got so far and then just see where we go next. Now, the square root is certainly an honorable function, but I think when we're doing calculus, it's probably best in most cases to replace things like square roots. Let's rewrite this as the integral of 2x to the 4 plus 3 to the power negative 1/2. It's almost always better when doing integrals to use fractional exponents rather than to use radical signs. Now, we're not quite done because I still have an x cubed here, an x cubed dx. Now upon substitution, I would have u to the negative 1/2 x cubed dx, but you see from above du is 8x cubed dx, and so I need an 8 in here if this piece is going to be the du that we found above. I can put an 8 inside if I put a 1/8 outside. That's just a multiplication by 1. And so now, making the final substitution, I would have a 1/8 times the integral u to the negative 1/2 du, because 8x cubed dx is exactly what du is. Well, I recognize this form. This is one of my things to know and remember, and that's the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus a constant, and there is a proviso on here. This is n not equal to negative 1. Well, in this case, of course, n is not equal to negative 1, but I think in the next problem it might be, so let's just keep that in mind. All right, then just using the substitution, this will turn out to be 1/8 u. Now raise the exponent negative 1/2 by 1, and I get positive 1/2. And then I have to divide by the new exponent, 1/2. Of course, dividing by 1/2 is the same as multiplying by 2, which would give me 2 over 8, or 1 over 4, u to the 1/2. And at some point, of course, I owe you a constant still, but I think I'm going to do the back substitution and then give you the constant. So let's erase this. and say that this is in fact equal to 1/4. Now the back substitution just is replacing u with what u stands for, which is 2x4 plus 3. And what's the exponent on u? Well, it's 1/2, and then plus a constant. And so there we've evaluated an integral by substitution. We were successful in our last effort, so let's push our luck and see if we can do another integral with substitution. Now here we have 1/x log x dx. Maybe a little more complicated because it has a log function in it. But let's use everything that we know and just proceed slowly, one step at a time, not get too excited, and see if we can't figure out what this is going to be. So we've got the integral sign, and I have a log x in the denominator. My preference is to use exponents whenever I can. I think it helps me see what's going to go on. So I'm going to put that log x to the power -1 rather than have it in the denominator. Now I've still got a 1/x dx. I now am looking for a substitution, but I see that I've got something in a parentheses raised to a power. So not always, but very often, that's a good candidate for my substitution. So if I would let, I'll substitute for u, if I would let u equal log x, then I have to get the differential next, so du would be equal to 1/x dx. So that would be my substitution. Now when I go back and I look at my integral, I see that I'm really in pretty darn good shape, because my integral has got a 1/x dx out here at the end, and that's just what du is going to be. And then I've got my u, well, it's in a parentheses raised to a power, so that's not going to cause me any problem. So let's go ahead and do our substitution and see if that maybe takes us to a next step. So this is going to be the log u, not the log, but the integral u to the power -1, and then 1/x dx is du. Okay, I would say that's in good shape. Now, the previous example, we just noted the power rule, but we also noted that on that power rule there was one proviso, that the exponent could not be -1. And that's because we have another rule that we would remember from 5 Things to Know that says the integral of 1/x dx is equal to the natural log of absolute x and then plus a constant. Taking indefinite integrals, we've always got that constant to add. So this is of the form 1/u, u to the -1 is the same thing. So let's just use this form right here and evaluate the integral u to the -1. The integral u to the -1 would be natural log, absolute value of u, plus a constant. And now all we have to do is back substitution, because remember u, what was our substitution? U is equal to natural log of x. And so now this becomes, doing back substitution, natural log, absolute value, natural log, absolute value x, plus a constant. So this is log, and I don't think this semester we've seen log, but there's no reason in the world why we can't take the logarithm of a logarithm. So this is a perfectly good example. And now we've done 2 examples by substitution, and that's probably enough for right now. Thank you.